I'm going to talk to you about an idea I had on how we can kind of regain a little bit of trust in the everyday computers we use. So, what is the problem? Well, the problem is basically these guys. I mean, the thing is, like, we all use computers in our lives. We use them for, I don't know what you use them for, but I use the most important thing I think I'm doing with my computer is actually talking to other people. I mean, yes, we are all watching videos, but, you know, talking to other people. And we do have quite a problem there, because even though we have developed quite a lot of solutions to make this talking to other people more secure and to actually hide from these guys what we are talking about, like all of these solutions, like for example GPG or OTR or Signal, like are executing in basically this. So this is a block diagram of a modern computer, in this case the Lenovo X230 I'm using to show this presentation to you. It's a kind of 3-year-old or something laptop based on an Intel CPU. And like as you can see from this block diagram, the thing is super complex. And the thing is that on this machine, I'm executing my GPG and everything is encrypted and everything is fine. The only problem is like the plain text of my emails, which I'm decrypting, even if I'm using something like a smart card, is going all over the place. So we have like a super complex system. We have like also in this case, the red highlighted things are like subsystems that contain some form of proprietary firmware which we cannot audit. And all of this makes it, I would say, pretty easy for a sufficiently well-funded attacker to actually attack that system. So now if we want to consider this system and like what we ultimately want from it. I mean, ultimately, I want to talk to my friend about computers because I like computers, and I generally use a keyboard to like type stuff, and then I click send, and then it gets sent and encrypted and decrypted, and on the other end, it's displayed on a screen as words, and my friend reads it. Now, the thing is that as you can see from that block diagram, I've highlighted like the parts that are involved, like that I actually need for that communication in green, like keyboard and display. If we say that, okay, at the display and at the keyboard, I basically need to use plain text because crypto glasses are not yet a thing, and also I cannot really type in RSA or something. So in the end, I kind of need to have plain text there. But on the other hand, I don't really want to trust all of that other stuff, especially like these things running untrusted firmware, like the things with red borders. The problem in that case is, like, since a couple of years now, Intel has gifted us something, namely CPUs and basically the platform controller hub, which is containing the integrated graphics, which are both running proprietary, pretty reverse engineering resistant firmware. So I have this CPU, I kind of need that because I want to encrypt stuff and decrypt stuff, but I don't really want that thing to be handling plain text. But on the other hand, like, I have no choice because you see all the arrows are pointing to it. There's no way around it. So we need to like think about where can we place that kind of trust boundary. And I think realistically there's really only one choice. And that is basically to place this trust boundary, like up to where do I want my plaintext to be and where do I want my ciphertext to start, right at the input and output devices. Because realistically, I don't think there's a terribly high chance that we will be like reverse engineering Intel management engine and embedded controller firmware for any practical number of platforms and keep it open for any number of years. So the places where we need to put this kind of encryption or something that makes it happen is in the display bus or display buses. In case of this laptop, that's primarily a LVDS bus, which is a digital display bus. On more modern devices, you would use embedded display port. which is basically very similar to LVDS, just with added protocol layers. It's like very high speed, but it's just plain pixel data, so there's not much encoding happening there. No video codecs or anything like that. And on the keyboard side of things, that is basically the embedded control, like this laptop and I think most other Lenovo devices, the embedded controller, which is some kind of management thing, which is doing basically everything they couldn't fit somewhere else, is basically scanning the keyboard continuously, and the keyboard is just really a dumb matrix of switches. So pretty much no active devices there, except for a couple of LEDs for like mute and power. So from this point of view, we need something in between of these components that will be receiving, hopefully, only untrusted ciphertext from Platform Controller Hub, which contains the integrated graphics, and the embedded controller, which contains the basically keyboard matrix scanning, and forward, like do some decryption there and encryption on the reverse path, and forward that to display and keyboard, which fortunately are pretty simple devices, so there's not much logic happening in there yet, if we ignore like embedded DisplayPort and HDCP and so on. So the thing is now, if we look at that block diagram, so you have like CPU, embedded controller, platform controller hub, the interceptor, the display keyboard, and these two pretty simple buses. That has a nice side effect of implementing a system that way, and that is that these two simple buses are used pretty widely. For example, this is a block diagram of what, in this case, Texas Instruments would like your smartphone to look like. It's pretty much the same for all vendors. They like basically just exchange like who makes the parts. They all do basically the same thing. You have like the CPU in the middle of this application processor, which in fact is a huge system on a chip. Like modern ones even include like packet-switched memory buses and stuff like that, so really advanced stuff. But in the end, that thing is only talking to your display via something either similar to LVDS, some are even using embedded DisplayPort, so like a high-speed serial protocol, but still pretty dumb. And I mean, you don't have a keyboard in most smartphones, but you have like a touch screen, and these touch screens are generally also controlled over like a pretty simple serial protocol like I2C. So we can definitely adapt the solution from before to also work in a case like this. You will obviously have like power management issues and form factor issues, but purely technically from the electronic and computer science side of things, this should work. So if we look at this block diagram of this general idea on how we could organize our computers, we have this interceptor device. Okay, so it needs to kind of do something with LVDS, like receive it, process it, send it back out, and do like something with the keyboard switch matrix scanning. Like how does this, like how would he actually control that from an application point of view, from software running on the host machine? Basically, this is the general idea I had for that. This is a diagram of what a frame sent from a basically any monitor standard today looks like. You have like this vertical sync and horizontal sync signals, which basically are framing information stemming from back when VGA was a thing. And then you have like the actual content area, where most of the time you have some kind of desktop environment running. And then you have like a application window inside that desktop, which may contain something worth protecting. As an example, think for example of Thunderbird, where I want to send like an encrypted email to my friend, or I want to receive an encrypted email from my friend. So in that case, Thunderbird is like running on my Linux system, displaying a window. In case of I'm receiving an encrypted email, that window is displaying like, basically, if I would not have like a nickmail or something installed, it would basically display like ASCII armored GPG binary. Now, what we need to do in this, to make this work in this scenario, is we have some kind of Thunderbird add-on which recognizes that I'm displaying like GPG armored GPG ciphertext, and which will take this GPG armor, like convert it back to binary form, and then formatted it as a simple bitmap. A bitmap that contains a special header at the front that tells the interceptor device something like the width and height of the bitmap and contains a authentication code, so cannot just anybody go and format bitmaps which would work with my interceptor device. And then I need to display that bitmap, which fortunately I can do on basically any operating system, any platform. And this bitmap is then interpreted by the interceptor and decrypted on the fly with my GPG key. The interceptor, since it has access to the keyboard and display, may ask me to input a passphrase or to, I don't know, insert a smart card or something, depending on the implementation. And the decrypted plaintext is then rendered into a pixel buffer, which is inserted in the live display data stream, basically at the same place where this payload was communicated before. So basically, if I'm running Thunderbird, I would make this add-on, so the entire window where I'm reading my email would be this payload area and contain the GPG ciphertext, and this interceptor would exchange that by the decrypted data in flight. Now, how would you actually make that work? The thing is, this interceptor needs to be able to process this really high-speed display buses, like LVDS, and do in-flight transformation on it. So that's a pretty hard task. And also we want it to be somewhat not too complex, so we can actually secure the thing itself. So we don't just replace one huge attack surface with another huge attack surface. Now the to me most obvious way to do this would be to use an FPGA for most of the stuff, because these things are basically very nicely suited for this application because they're really good at handling large bandwidth, high bandwidth, high frequency data, like in display bus. And yeah, this is basically how I would imagine such an FPGA-based interceptor to work. By the way, sorry for the non-planar graph thing. So, without looking too much into it, we can already see that we have an advantage against this x86 platform, like the Lenovo X230 here, in that we have we do still have a lot of components, but they are not that. They're not that centralized. There is some factor of compartmentalization there. So I have, for example, for example, if you consider the display data path, if my display signal does not contain any payload, any headers, any special markers, and it's just regular display data, then it will go in this diagram. It will go in on the bottom right side, which is basically from the untrusted domain from the platform controller hub on Intel platforms. It will go through a LVDS deserializer, which basically converts it into a lower frequency signal for FPGA internal use. That will go into a pattern detector. Now, if that pattern detector does not detect this special marker header I put in front of my GPG payload, it will not do anything. It will just pass on the signal. The signal will then go through a frame buffer for clock reasons. Then it will go through a buffer switch, which in this case also does nothing because there's no payload there, so there's nothing to replace. And then back to a serializer. And the interesting thing is that at no point this high bandwidth display data signal, which may contain other sensitive information I don't want the interceptor to know, at no point does it even touch anything apart from some relatively simple parts of digital logic. So it's not going through any kind of CPU or higher level processing. It's basically just a bunch of shift registers, pattern matching, and a couple of buffers. So in this way, I can organize this system so that sensitive data is really only touching parts it absolutely needs to touch. From an electrical point of view, there's on the FPGA separate buses for this kind of data. And this way, I can kind of reduce the attack surface of that somehow, somewhat. So let's consider now the case of a frame that contains actual encrypted payload data. Now, the key for this data is in the, like depending on the implementation, either in the FPGA itself or in a external secure access module, so basically a smart card. And the CPU and graphics processor which formatted that data for me do not know that key, so they can't decrypt it. They're just running basically a bitmap graphic. And now the pattern detector in this device will, when it's receiving this data, recognize that header which was previously formatted. And then it will go on and write the payload, in this case like probably some lightweight protocol and then the actual GPG data into a payload buffer. And upon completion, it will notify something I called the application processor, because basically I think you will probably need something like that. And this application processor will then do processing on that. Like, in fact, what it will do in the GPG use case is it will probably do some protocol decoding, then extract the actual cryptographic payload, send that on to a crypto coprocessor. I think it makes sense to distinguish these two things here because the application processor, like for most things, you don't need like any kind of cryptographic acceleration. And on the other hand, maybe you don't want the thing that is handling all the complex protocol logic to actually also do the encryption and decryption and handling of plain text. And this crypto coprocessor would then decrypt this payload, possibly with the help of a smart card secure access module, and will then forward the plain text via a separate data path to the renderer. So physically, the application processor in this scenario would never be in possession of the plain text. So even if you compromise it through some way, some means, you would not be able to access plain text data there. And the renderer would be a piece of basically probably another processor, realistically probably running something like FreeType that is converting like UTF-8 input into pixel data, which, as it turns out, is a really complex problem, but I will be coming back to that later. And this renderer is then like outputting a bitmap into a render buffer, and this render buffer is then dynamically switched into the in-flight LVDS or embedded DisplayPort signal by this buffer switch thing. So the buffer switch basically just needs like the position where to flip between upstream display content and the render buffer, and it will count the position in X and Y coordinates and then switch over and switch back. Now, this nice thing about like this entire compartmentalization thing is that it enables also some kind of some neat security features. For example, one thing you can do is for the you see the render has two inputs. Like the application processor may want to render some kind of user interface, so like a password prompt or I don't know, some message. And on the other hand, like the crypto coprocessor wants to render like plain text data. So in this case, since the renderer is getting two different data streams, it could, for example, color code it. So as to make like spoofing of, for example, application processor messages by like having a ciphertext decrypted in the device a little harder. So you kind of know that if the text is blue, it's the application processor, the interceptor directly talking to you, and if the text is like red or something, it's like a decrypted email you're reading. Now, if in this scenario, so now I can like decrypt and securely display GPG emails. Now, assuming I want to actually write an email, how would I do that? Well, in this case, basically what you would have is you have this keyboard decoder and emulator on the top and bottom. So you have like the decoder, which is reading out my physical mechanical keyboard, and the emulator is then simulating another mechanical keyboard to the rest of the system. Like implementation detail for X230 would be that you can have like the function key, which is wired into the rest of the system as a physical data line instead of like multiplexed data lines. You could have that like as a electrical override, so that this keyboard emulator can only actually emulate the keyboard when you are pressing that key, so as to like still make it a little harder to exploit that in order to like, I don't know, enter commands into a root shell or something. And the workflow would basically be like this. I would press, like I would start up Thunderbird, start writing an email, and then when my cursor is in the editing field, I would, for example, press a certain key combination which tells this interceptor device and the application processor within it to display me basically a very simple text editor. It just needs to be complex enough that I can enter text in a language of my choice and to be internally representing that text as some kind of UTF-8. Now, I enter my email message into this application processor, and then I would press, in this case, a certain key combination for example, either I could choose the recipient key ID, or I could possibly also communicate that from a Thunderbird extension. That is highly implementation dependent, but in the end, the application processor would send the plaintext to the crypto processor, which would then input the encrypted ASCII-armored GPG ciphertext via the keyboard emulator into my actual email client. Now, another interesting thing is that here the crypto, nobody but the crypto coprocessor doesn't need any access whatsoever to the keyboard emulator, because basically I can't think of a reason why the application processor would want to push keys on my keyboard. So in this case, I can have the crypto coprocessor having exclusive access to the keyboard emulator, and then it is entering this ciphertext as if I would be typing GPG really fast. And my email client, in this case, wouldn't even necessarily have to know about that, because for it, it's just a keyboard. Also, a nice thing about it is you don't need any operating system level drivers. You may not even need application level support for it. For example, you could have parts of this this bitmap formatting running in the cloud or something, on a different machine which you trust more. So now we have a physical device which can do some kind of encoding, encrypting and decrypting of data, and which in order to do that has to do key management. And I mean, putting a smart card next to it, I don't think it's a terrible idea, but still, that doesn't look too secure to me. Also, I have the advantage that, compared to a full x86 main board, this system is pretty simple. You could probably do it with a 4-layer PCB. So this is actually within the realm of possibility for a hobbyist to solder themselves. So I think one thing we should seriously consider there is taking that concept and making this device into an actual hardware security module, as they are usually used to store SSL certificates and so on, because they are not actually that complex to build, I think, and that would present a much higher hurdle for an attacker to actually pull any plaintext or key data out of that system, because suddenly in a hardware security module is basically you have a intrusion detection feature on the circuit, whereby the circuit detects when you open the case or drill holes in it or remove it from the device, and you have a backup battery that keeps that online no matter what happens. And the interesting thing about making a hardware security module out of that would be that you could, for example, have it actively wipe a key when it detects that the case is being opened, either the case of the hardware security module itself or even just the laptop. So, talking about hardware security modules, how would we actually do that? Now, I have actually disassembled a couple of those myself. So, generally, most hardware security modules that I actually use today basically consist of some kind of CPU and some memory and some SRAM, which is used for key storage. And all of that is put in a box. And on the inside of that case box, there is a so-called mesh printed. This is basically just two PCB tracks printed on the inside of the case, snaking their way all around it, contacting the main PCB at a couple of points. And now there is a part of the circuit inside the hardware security module that is continuously monitoring these traces, whether they are broken. And the idea is that in order to get to the keys which are in the memory inside, you need to first open the case, and to do that, you need to break these tracks because they are all over the place and you can't drill a hole in it without breaking them. Now, I think that can be done pretty easily and it's pretty effective. For example, one of the more effective approaches I've seen in practice so far is like basically a flexible plastic foil, which is printed with some kind of silver ink. It's basically exactly the same material you find inside really cheap keyboards, you know, these rubber dome things. And that stuff was just wrapped around the PCB on all corners. And then everything was potted with a kind of little flexible but really chemically resistant potting material, like epoxy resin. And now, as soon as you would try to remove that, it would totally rip apart these sensible traces on that plastic foil. I think that's a nice approach. I think there's a couple of other things I would kind of like to try. So like one thing is RF interference. So you have like a metal can instead of plastic case, and you have like just wire randomly stuffed into it, so you can't really predict where the wire is, and then you have it potted, and then you continuously measure the frequency response basically of the different wires and traces within that case against each other, the coupling between them, and measure when that significantly changes. Now, whether that works in practice, I don't know. It would probably be pretty expensive, but it might be worthwhile to at least explore it. I could also imagine like using some kind of ultrasonic measurement. So you have like a potted device, and on the main circuit board you have a couple of small ultrasonic piezo transducers, and you are sending like ultrasonic through the physical like the potting material, and you are measuring if that response does change at all. I think that might actually be pretty effective, because in order to like open it or do anything to it, you would actually need to like touch it. And if you like, maybe you could use a laser against it or something. I don't know. Like, advantage of that would be that it would be pretty cheap, though this may come with like high current consumption. Another approach that I would like to try out is like triboluminescence. So basically you put a couple of photodiodes, so like really sensitive light detectors, on the PCB itself. And then you encase everything with a clear potting material that is like mixed with like so-called like friction glow or smash glow crystals. Like there are certain chemical substances which in crystal form will emit a bright flash when you break the crystal, or when you rub two crystals against each other. And now if you would have that inside the potting material, I think it would be really hard to, like, in some way, if the potting material is like chemically resistant, in some way like remove the potting material without exerting mechanical force on these crystals, which would cause them to flash, and you could detect that with the photodiode and wipe all keys. Yeah, so these are like just ideas what you could do in order to make this hardware security module like at least moderately resistant against an attacker. I mean, they are not bulletproof. Like any hardware security module out there can be breached with sufficient resources. But the thing is, from all I've seen, this would probably already be like more than than at least like most commercially available hardware security modules provide. I know some military stuff then like detonates the device, but yeah, we kind of don't want to do that, I think. So now I've like praised like this new idea for a device I have, which I want to put into a laptop. Now, one thing we need to consider there is like you're adding an additional piece of like complex piece of circuitry inside a thing in order to, in the end, reduce attack surface. So like what attack surface does this device itself provide? So like, this is not an exhaustive list, but it's like things that I think are probably pretty critical. Like one is, you need some kind of protocol decoding in that thing. You need to like find this header in the in-flight display signal. You need to like parse GPG payloads. You need to probably do some state handling on top of that. So that would definitely be a complex part, and there is some potential there to like construct invalid payloads which may affect the state of the system in some unintended way. Now, the countermeasure I would propose for that is keeping it as simple as possible. The nice thing is, since it's in hardware, we can kind of do that. We don't need to like configure a million registers in order to make some video input core on some system on chip working. We can just exactly put into this piece of like FPGA fabric what we need and nothing more. And also we have like some of that protocol handling running in like, not really running, but implemented in physical hardware circuits. And these are generally like, you can't probably like fuzz around with the state there, but you can probably not, or it will probably be harder than on a CPU to actually persistently modify the state in any useful way for an attacker. There's the social engineering vector. Now, yeah, the thing is, this would definitely be targeted at like pretty capable people, like not really average users, so like people like you. So I guess in the end, social engineering will probably not be a terribly large, important attack scenario, since in my experience, like people like sufficiently knowledgeable about computers somewhat decrease in their being susceptible to social engineering attacks. Physical compromise is obviously an issue. Like what happens if somebody can like open the hardware security module without it noticing? Yeah, well, the thing is, I think we can not terribly eliminate that, but we can at least make it a little harder with this limited hardware security model stuff. I put an FPGA vector up there because it was kind of like a highly published topic, at least in like security research there. Now the thing is, I don't think a FPGA vector in this instance is super realistic, because I think it will be really hard to bake something into an FPGA that will actually provide any useful like compromise in that scenario. Logic flaws, well, obviously you can have like logic flaws within the device. So I think we can do some stuff against that. So the thing is that since we are implementing our own hardware there, we can like do some more countermeasures than you can do purely in software. We can, for example, have the code in a physically read-only memory, so it cannot be modified no matter what. We can have like independent memories for different things, like a memory for stack, a memory for heap, a memory for code, and like have lots of arrows if you try to do accesses across their boundaries. We can do some like primitive separation of tasks into different CPUs, like basic crypto and application and rendering is, I think, like 3 major areas I can think of. We can do some hardware level access enforcement on places where we need to share resources. For example, in the FPGA implementation, we will probably have a common DRAM external for all the pixel data, but we can like securely separate that by like hardware level access enforcement, so like the different components cannot write into their respective address spaces. We can generally keep it simple. So if it's like too complex, it will be, I think, really hard to keep it secure. But if we keep this super simple, at least compared to a full-blown x86 platform, I think we can actually keep the attack surface within the manageable area and actually audit the thing to a meaningful extent. Like one thing I would like to note here is that, for example, for the CPUs, one thing that would really lend itself to it would be the RISC-V project, who are currently like actively working on a basically entirely open source CPU that is pretty well specified, pretty well tested. Like there are even some efforts to actually prove it, that it works, like logically prove the functioning of it. And there's also some work on, for example, tagged memory and other like hardware level security mechanisms there. Like another thing I would like to point out is that since all of these parts of this system are operating at a very low level, we can just reset everything really frequently. It's not bulletproof, but it can at least make attackers' lives harder. Because if we like reset the entire state of the system, like everything but the actual keys, every frame or something, or every time a new payload is received, it will be much harder for an attacker to actually compromise the state and bring it to any new state that is useful to the attacker. It will not like prevent anything, but it will at least like make the practical exploitation harder. Now, considering this attack surface, like what would be practical scenarios with this device in a laptop and with the same laptop without that device? So I just wrote down a couple of those, and I made little colorful check marks on how it would perform. Obviously, this is not absolute. It like depends on the implementation and on how you're particularly using it. But I think as a general guidance, this should perform quite well. So like in the lost device case, for example, if you don't have this kind of interceptor inside the device, you can already get pretty secure solutions if you're using secure boot correctly, if you're encrypting your hard disk, if you are storing your GPG keys in some kind of secure memory, and so on. But it depends on the implementation. And like with this interceptor device, I think it will be a little easier to actually make sure that if you lose the device, neither the keys themselves nor any plain text can leak the device. Now, second scenario is like unlocked device stolen. So somebody comes and takes your laptop away while you're working at it, and you don't have time to lock the screen. Now, the thing is, fundamentally, you will have the same problem if you kind of unlock this interceptor device over a period of time. But the thing is that since you only need this interceptor device in order to decrypt and encrypt emails, and you don't do that all the time, you can have it locked most of the time that your screen is unlocked. Also, since this interceptor device is like hardware we are building ourselves, we can include additional security features that are not offered in off-the-shelf laptops. For example, we could have like some capacitive sensor in the palm rest that is detecting when like your hands are removed from it, and that will just wipe the keys in that case. And then you need to re-enter your password. That would be too annoying for something that would lock the screen, but like for wiping, clearing a GPG keyring, for example, that might be a adequate trade-off. Now, targeted attack, or what I described as targeted attack, is basically somebody with a lot of money really doesn't like you. So, for example, somebody specifically wants your email. Now, without an interceptor, you really have a problem, because even if you're using like CubesOS and you're encrypting everything with the GPG, in the end, you have a off-the-shelf Linux operating system with a Xen hypervisor running on a x86 platform with lots of proprietary firmware, and many places there are handling plain text data. And also, this system, the entire stack, is so complex that I think it's practically guaranteed for every part of it that there will be flaws found. And we see that all the time. For example, Apple's iPhone has a really good security architecture, but it's still pretty complex, and people are getting around it. Also, for example, the Xen hypervisor, which is underlying CubesOS, which is the primary isolation feature there. That thing is also highly regarded. Still, there have been flaws found in it, because it is a huge, complex thing. And I think we can lower that attack surface by basically concentrating it on this interceptor device, which really only presents very simple interfaces to the outside world, which I think might be easier to actually audit. Now, an obvious failure scenario for like both things, like a laptop with or without this device, would be like you are bugged. So like somebody places a camera behind you in your your apartment or something. Because, like, since you need plain text data coming out of your screen at your eyes, since we don't have crypto glasses, like anybody in the same room will be able to kind of film that. Like, even if you're using like one of these privacy filter things, like at the right angle, people will be able to read it. So, in that scenario, obviously, any mechanism that still uses a display will fail. You may like use some kind of Snowden cloak or something, but yeah, I think that would be really hard. Physical access, so like somebody has temporary physical access to your device, like during shipping or at a border checkpoint. In that case, I think it depends in any instance, because without interceptor, well, maybe they can like install a rootkit, exchange your boot flash, or something with the interceptor, well, maybe they can place an interceptor in front of the interceptor or something. You know, like there's really nothing you can do there if you don't even know whether you're getting the same laptop back or whether it's like I don't know, some SIM device which is just like which includes like monitoring for CPU and for keyboard and display. So I think in that case, like we can make it a little bit harder by having like these hardware security modules features to like detect when the case is open, so we can like provide some incentive against like opening the case and messing around in the system there, but it won't be bulletproof. Like total communication surveillance as it is happening in practice, I guess that like any system is basically secure in the way that we are leaking metadata. We are leaking metadata. It's really hard to avoid that. The difference is with the interceptor, you're also just leaking metadata instead of plain text to your operating system. But that might not be like for communication surveillance. That's irrelevant. Now, what needs to be considered, of course, is that by placing an additional device in your laptop, you are actually from a whole system point of view, you are increasing attack surface. And if that device, like this interceptor, would be compromised, that would be totally game over, because it has access to your two most privileged things in the laptop, like the display output and the keyboard input. So basically, any secrets you communicate to your computer are there on these buses. So I think that we need to be really careful implementing this in order to not make this an actual security, a security threat instead of a security feature. Major tasks I think we need to solve in order to actually make this practical are basically disassembling and reassembling this embedded DisplayPort and LVDS stuff, because as it turns out, it's not easy. If you have some expertise in that, I'm really interested in feedback and suggestions there. I think rendering Unicode will be hard. I mean, we want people to actually be able to communicate in any number of languages with this device, and actually supporting Unicode font rendering on a embedded thing, and that in a secure way, I don't think that will be trivial. Then we need to define this packet payload format in a secure way, so like it doesn't provide too much complexity. We need to get the keyboard pass-through semantics right, so you don't accidentally input sensitive data into your host machine without you really noticing it. We need to split like this, do this entire privilege separation, like crypto coprocessor versus application processor, in some sensible way that we actually gain something by it, and we don't have like a huge amount of code running in the crypto coprocessor, for example. And I think if we want to implement this with a smart card as a key store, like long-term key storage, it will probably also be hard to get that right, because I don't think as a private citizen you can just go out there, buy a smart card software development kit and write your own RSA 4096 like GPG key handling on the smart card. So we may need to figure something out there if we want to do that. Now, I don't know. I hope I could actually I could make you interested in that idea. If you have like any feedback, any suggestions, any ideas, or like some expertise even in the relevant fields, I'm really interested in feedback and help with this. I'm reachable at like that email address, the GPG key is below, and this talk, like the slides, will be on the GitHub repository up there, so you can also just give feedback by raising an issue there if you have something. Thank you for listening. Now, everybody who I haven't bored too hard, I think we can do a question and answer session now.
Yeah, thank you very much. That was enlightening. That takes us to the Q&A. There are 2 microphones set up here. Please form an orderly queue. I'll try to make sure that I realize who's first. And we will just wait for the people filing out for a second, I think, because we got enough time, don't we?
I think so.
Great.
Yeah, 10 minutes. Q and answer.
I think he'll pick me.
Okay, fangen wir jetzt links an. Fertig. Okay, we start at that mic and then ping pong to the room.
Yeah. So as far as I understand, the idea of the interceptor on the keyboard side is that plain text goes in, ciphertext comes out.
Yes.
All right. So I would like to edit all of my emails in Emacs or Vim with all of the fancy packages I found online.
Obviously, we will need to compromise like some amount of usability there, except if you want like a full Emacs instance running in that interceptor. I mean, technically it's possible.
Yeah.
You can, like in these FPGAs, you can actually, like the development system I'm using, you can actually run a full Linux in there, but I don't think you would want that because it would pose like some attack surface, I think.
Yeah. More generally, the benefits of having your applications in software rather than hardware is that you can update them. Also new crypto protocols, better encodings than UTF-8. All of that is lost in your design, yes? Or
Well,
most of it.
could you maybe make the monitors a little louder? I can barely understand him. So
Should I repeat? Shall I repeat the question? Or you got it?
So like updatability of the firmware.
Yeah. You lose the benefits.
I mean, the thing is, you can like, if it is implemented in an FPGA and not in an ASIC, you can actually easily update it. I think it is very sensible to make it as hard as possible to actually do that in practice. Like you need to open the hardware security module and like flip some switch or place a jumper or something, as to make it impossible to do that via a software-only attack, for example. And like, if you do that, well, yeah, you could update it. Okay, yeah.
Okay, how do you actually know that what you're seeing is coming from the interceptor, and how do you know that when you're typing, it's actually being intercepted and not going to the Intel hardware?
Nice question. So I don't actually know that what I'm seeing. Oh, okay. Well, it depends. Like I cannot absolutely know it because somebody could have placed like an interceptor between me and the interceptor. Now, this like I think the other way to talk about it is like. What I want to have is I don't want an application on my operating system being able to spoof interceptor output. I think one way to make that is to have the the easiest way to implement that in practice would be to have just the interceptor always in full screen and use one of the physical LEDs on the keyboard of a ThinkPad in order to like signify whether input and output is coming from and going into the interceptor or from the underlying device. So you have like you could repurpose the mic mute LED or the mute LED for that. Other possibilities would be like for the output case to like draw a border around the screen, and if it's red, it means like Linux talking. If it's green, it means like interceptor talking. For the input, basically the same thing. You could have some like visual clue. I think the input case will be pretty hard, like in order to get that right, will be pretty hard because we don't want you to accidentally input a password. And if you input a password often, you don't necessarily care that much about the screen while you're typing it. So I think a visual clue might even be not enough in that case.
Well, I guess we finally found a good use for the ThinkVantage button.
Well, except that one can be controlled from the CPU.
Yeah, somebody mapped it to Newt on. Okay, anyway, we invented the Signal Angel. The internet is talking to us.
Yeah, so the first question is, would the interceptor work in a way KVM does? So instead of adding a chip to the main board, you put a box next to the computer into which you plug the keyboard and the display, and the box just presents the encrypted input to the computer.
Definitely. Like in a desktop use case, that would definitely be how I would implement it. In the laptop use case, obviously it's tempting to actually include it inside the actual case. For example, in X230, we could just replace the hard disk with a smaller SSD and use the free space there, because it's already quite close to the display and keyboard connections.
Okay.
Hi, I really like the creative idea, but I was wondering how you feel about. I mean, you touched upon the RISC CPU implementation that
RISC-V, not OpenRISC.
Sorry.
RISC-V.
RISC-V.
Yeah.
Okay, I'm not sure, but there's a university in England where they are doing research on an open architecture.
Yeah.
If you go towards that direction, how do you feel about having a system on its own that you can trust, instead of having an implementation in a regular machine?
I think that would be really interesting. Like that is one of the more interesting points of actually doing this. I mean, the thing is, you can still use like all the amenities of your operating system with like compass wobbly windows and like Windows Aero Glass, depending on the operating system. But you also get like this trust aspect from the CPU implemented in the FPGA. So, like for a start, I would definitely keep the firmware running inside it as simple as possible, in order to avoid like making a crash and like avoid like adding an attack surface there. But yeah, of course, like long term, you might want to add more functionality into it with sufficient isolation, of course.
Okay, thank you.
Okay, the internet is added again.
Thanks. Just a short question. What about USB keyboards?
Yeah, well, it depends. Like, if you have some means of plugging that into the interceptor, no issue. Like, USB is still simple enough that you could implement it with some effort on an FPGA, like both host and device ports. In the laptop use case, I don't think it will be that easy because you would need to intercept like all the USB ports.
I understand that the whole point of a device like this is to bring about something like the crypto goggles you mentioned at the beginning, but in a more limited fashion. However, it does seem like there's opportunity for the solution that you've proposed to have integration points for operating systems like Gnode and CubesOS and so on and so forth. Do you think that there's another angle? This is a different thing that you can isolate? Or is this the only way in which it can be done? And if this is the only way in which it can be done, the things that you propose that should be done, are there any integration points for operating systems like that?
I mean, I don't think this is the only way you could do something like this. For example, you could also, like, for a much, like, from a implementation point of view, much simpler architecture, you could just have a device plugged into your USB port which has a display and a keyboard, like, separate to your regular display and keyboard. Like, the only difference would be it would be a little less convenient to use. So I think there are many other ways to do it. I think the intercepting the actual display data thing is kind of interesting because it's pretty portable across platforms. As for integration points for like the operating system, especially something like Cubes, I think there's a lot of potential. I mean, I didn't think about that much yet because
think about like anti-evil made being integrated with the system that you're talking about. It would made for a pretty resistant system that cannot be spoofed.
Yeah, I mean, you could also, for example, you could even in case of Cubes, you could integrate some of that. I think you could actually integrate into the display manager in order to have like both Cubes and the interceptor cooperating. So like Cubes knows what the interceptor is doing and can actually, for example, you could maybe handle the inputting your password into the wrong device thing there. Okay, whatever. That was my screensaver.
Okay, there's another one from the internet.
Yeah, what about ciphertexts that are longer than what would fit on my screen?
Nice question. Like the same thing goes, by the way, for plain text that is longer than what fits on the screen. Like I didn't touch upon that too much, but basically what you would do is you would spread it across different frames. Since the actual pixel bandwidth, the bandwidth of pixel data on a even on a low resolution display, like the shitty display of that laptop, is like already in the gigabit per second range. So no matter how long your emails are or what amount of ciphertext you are outputting there, you will be able to like stuff it into consecutive frames, you will have some like processing limitations on the FPGA because it's like probably clocked very slowly, and you will be, have some like memory limitations also. But like I think for a general system, at the cost of a slightly higher complexity of the protocol handling in the interceptor, this can be solved. And for the output case, like you just scroll. You just need to wire like the up and down arrows or screen up and screen down keys to like the renderer or something.
Thank you.
Okay, so your main argument was that your system is less complex and therefore less attackable. But then I wonder why you make the effort of intercepting your LVDS traffic. So, like, from my experience, I guess that about 90% of the complexity of that system will be on intercepting the display data. So if you want to have something plain and simple and with a low attack surface, why you don't use just an industry standard 4x20 LCD display and just intercept the keyboard line? This would be doable in like 1 or 2 days, and you could even let it run on an STM32. No need for an FPGA.
Yeah. But that would be boring. No, seriously. I think the like doing the live interception of display data has a serious usability advantage in that you can like. In my laptop use case, I have this. The laptop looks exactly the same as before, except for providing me this higher assurance for like certain operations. Like with any kind of external device, I would need to carry that around, need to tether it, and then like use 2 different keyboards and 2 different displays for different things. And like, I think for serious email reading, at some point you would want like a serious display on that thing. And on that, at that point, it gets just as complicated. Also, considering the development time, yes, intercepting LVDS and embedded DisplayPort is a lot of work, but that's not because it's super complex, but because it needs to be tuned pretty exactly, because you need to take care of a lot of details there, like phase alignment and stuff like that.
Okay, thanks. Next question.
How exactly do you think there's going to be something on the CPU sending your text away or whatever doing with it? And if there would be something like that, why do you think it would pass something like Wireshark listening on the network?
I mean, if you have like some kind of spyware running on your operating system, intercepting, for example, GPG or encrypted emails before encryption, you might not actually be able to discern that even using Wireshark if that spyware is any good. Like if it's any good, it will probably be using like some steganographic techniques in order to hide its own traffic inside your usual traffic. So you can't easily detect it.
Okay, thank you.
Okay, so I understood your proposal is also for writing email. And with that, so if you're hitting on a key, it's doing something, encoding it, encrypting it, and putting it in a buffer for the operating system to pick it up, to place it in the application buffer, right? So if that is correct, what kind of encryption do you plan to do on the actual key pressing? So if it's your own public key, how do you actually send an encrypted email to somebody else with their public key?
That highly depends on the implementation. Like my first approach would be to try to extend enigmail. So if you open an email, you're typing like the recipient in plain text because that is metadata anyway. And then enigmail will use like the same payload format in order to provide the public key of the recipient, ideally with the signature of your own private key to the interceptor. So that thing can actually then display the key, like the key ID of the recipient as validated by your own signature, with the key that in its private, with the private key that is only contained within the interceptor. It's a little awkward, but suppose it can be done. Another way would be to do the entire key management in the interceptor. So you kind of press a key combination and a menu pops up, and you then like choose the recipient's email address by typing it in there.
Okay, we got time for one more question.
Not really a question. I think you have found a good use case for the touch bar on MacBook Pro.
Well, it's good for Newt too. One more serious question.
I missed the beginning of the talk, so is this already like ready? Do you have a prototype ready?
I wish.
Okay, so at this point, I have 2 small Raspberry Pi Zeros in my laptop, and I'm able to close it perfectly. And so this is what I'm trying to do exactly what you're doing, but I'm planning on having one control, or control the keyboard, and then one control the networking, so that way I can segregate those out. So have you thought about, maybe something like that?
Yeah, I mean, the thing is, I would like to avoid like ARM socks, like system on a chips, because all of them, like Broadcom, Qualcomm, Texas Instruments, I've seen some of the insides of them, and it's not pretty. Like, it's super complex, and I don't think they're any easier to secure than the Linux you're running. Like Qualcomm, for example, making ARM socks just had like several serious breaches of their hypervisor and trust zone security in the last months. So I think we can basically rule out like any modern ARM sock.
Well, thanks everybody.